For years, whenever you opened your browser to check your bank balance or send an email, you looked for one universal symbol of safety, the little padlock icon in the corner. That tiny lock told you your connection was encrypted. It meant your banking details, your private messages, and your login credentials were mathematically secure from anyone trying to eavesdrop on the network. Then, in April 2014, researchers found a microscopic flaw buried deep inside that exact encryption system. It was quietly exposing sensitive data across the entire global internet. The most alarming detail was the timeline. Security teams realized this vulnerability had been sitting completely unnoticed in the core code for more than 2 years before anyone spotted it. This single coding mistake, known as Heartbleed, compromised the underlying security model of the modern web. Modern digital infrastructure relies on secure encryption protocols to function. These protocols scramble your data into unreadable text while it travels between your computer and a server. To handle this massive computing task, the internet relies on OpenSSL. It is a free, open-source software library that acts as the invisible engine for secure routing. The scale of OpenSSL's deployment was massive. Major tech companies, huge international banks, and government databases all integrated it directly into their systems to lock their digital doors. The world's most powerful institutions had built their digital vaults on a foundation that harbored a catastrophic hidden flaw. To understand how the flaw worked, we have to look at a routine check-in feature called the Heartbeat extension. It was designed to keep secure connections alive, so your computer wouldn't have to constantly renegotiate encryption keys. Normally, this works like an echo. A computer sends a short word, like Apple, explicitly telling the server it's 5 characters long. The server allocates 5 characters of memory and echoes Apple back to the client. But the code written for this heartbeat check lacked one critical safeguard. The server was programmed to trust the client's reported word length without ever actually verifying it. Missing that single verification step created an exploitable blind spot deep inside the server's core logic. An attacker exploits this with a lie. They send the word Apple, manipulating the packet to claim it's 500 characters long. The server complies, allocating 500 characters. It reads Apple, then fills the remaining space by overreading its active memory, spilling it to the attacker. That adjacent active memory is where servers temporarily store the internet's most closely guarded secrets. A single spill could contain usernames, session cookies, private messages, and even the master encryption keys used to secure the server itself. Because the heartbeat check is a routine background function, attackers could automate this lie. They could silently pull chunks of sensitive data from the server continuously, siphoning active memory piece by piece. To the server's security monitors, this looked exactly like a standard connection request. The theft left absolutely no traces in the server logs. Hackers discovered a mechanism to siphon the internet's secrets without ever tripping a single security alarm. When the vulnerability was finally disclosed in 2014, the cybersecurity world went into emergency mode. IT professionals realized a massive portion of active servers were running vulnerable versions of OpenSSL. As you can see in this public notice, institutions like the Canada Revenue Agency were forced to post warning banners and shut down taxpayer portals to stop the bleeding. Organizations worldwide scrambled to contain the threat. They patched servers, replaced security certificates, and ordered immediate password resets. The true concern for these security teams was the 2-year timeline. Because the bug had existed in the wild for so long, nobody could be certain if attackers had already quietly stolen their core encryption keys. This crisis fractured the trust model of secure internet communication. The guarantee provided by the padlock icon was broken. Heartbleed also exposed a stark economic reality. The multi-billion-dollar global infrastructure of the internet heavily depended on a piece of free software, maintained by a tiny, underfunded team of volunteers. The scale of the near miss forced organizations to change how they operate. Tech giants began funding critical open-source projects, auditing legacy software, and improving their vulnerability management. Yet, despite these industry changes, the fear of the unknown persists. Cybersecurity experts know there are millions of lines of old code still running deep inside our digital infrastructure. Heartbleed demonstrated that the security of the digital world can be shattered by nothing more than a single silent line of broken code hiding inside the software we trust the most.